All right, let's jump straight into this explainer. When we think about oil and gas, we usually picture massive steel platforms, right? Or rigs sitting out in a field somewhere. But there's this entire invisible world straight beneath the waves, an incredibly complex, highly pressurized universe operating in pitch black. Today, we're figuring out why that subsea world even exists, and honestly, why subsea engineering is way less like traditional construction and a whole lot more like designing a spacecraft for an alien world.
Think about this. Back in 1947, a well was completed off Louisiana in just 15 feet of water. A guy could literally stand right next to the wellhead. Fast forward to today, and we're completing wells in water up to 10,000 feet deep. At that depth, the pressure would crush a car like an empty soda can, so obviously nobody's walking down there anymore. Every single thing we do, drilling, control, interventions, it all has to happen through machines operated from a control room miles away, and it has to work perfectly on the very first try. That right there is the whole essence of subsea engineering.
So here's our roadmap for today. We'll start with the Deepwater Challenge, then break down the anatomy of subsea systems. After that, we'll look at the spacecraft design philosophy, dive into quality gates and testing, and finally wrap up with the wild economics of the deep.
Kicking things off with Section 1, the Deepwater Challenge, pushing past the shallows.
Why exactly are we out here in the abyss? Well, oil and gas still supply roughly 80% of the world's energy demand. And the industry didn't just wake up one day and decide to tackle extreme deepwater environments for the fun of it. It's an absolute necessity. Since about 1995, our shallow water reserves have been depleting incredibly fast. To keep up with that massive 80% global demand, we've basically been forced off the comfortable continental shelves and pushed way out into the deepwater frontiers.
Now, you might be wondering, instead of building all this crazy remote infrastructure, why not just send highly trained divers down a bit further? I mean, we've got advanced diving suits and submersibles, right?
Well, think about what happens to the human body under that much water. Once we cross roughly 300 feet, we are totally past safe diver depth. Below that line, every single intervention has to be remote. Taking humans out of the equation isn't a design preference. It's literally the only physically viable option we have to survive that kind of extreme ocean pressure.
Moving on to Section 2, Anatomy of Subsea Systems. Let's look at the mechanical body.
So if humans are out, how on earth do we get fluid from thousands of feet underground all the way to a host facility on the surface? Think of a subsea field like a human body. The wellhead and the subsea tree, that's the mouth, where the fluid enters our system. Then you have manifolds and jumpers acting like our veins, routing and combining the flow. Next is the umbilical, which is absolutely the nervous system. It's this massive cable carrying every electrical command, hydraulic power, and chemical inhibitor the field desperately needs so it doesn't freeze up. And finally, the riser is the spine, carrying all that valuable fluid thousands of feet straight up to the surface. Technically, all these parts together form a subsea production system. We're talking drilling, trees, umbilicals, manifolds, tie-ins, controls, and installation. And here's the kicker. These are not separate, isolated projects. If you change the water depth, you have to change your riser. Changing the riser means you need a different host facility, which totally rewires your entire control philosophy. Absolutely nothing in subsea engineering is designed in a vacuum. Everything has to be perfectly integrated.
Which brings us to Section 3, the spacecraft design philosophy, designing for the void. Because everything is so interconnected, it requires a massive mindset shift. A lot of new engineers jump in thinking subsea is just offshore engineering, but, wetter. Actually, scratch that. It is an entirely different philosophy altogether, driven completely by total inaccessibility. Designing a subsea system is exactly like designing a spacecraft. You do not get a service call. If a wire comes loose on a satellite, you can't exactly send a mechanic up into orbit. Subsea is exactly the same, except instead of the vacuum of space, you're fighting freezing temps and bone-crushing pressure.
Because we have absolutely zero access once it's down there. Every single failure mode that could possibly happen over a 20-year lifespan has to be anticipated on the drawing board today. Failure at the bottom of the ocean is a non-starter. So we either design the failure out completely, we build in massive redundancy so a backup kicks in immediately, or we make sure it can be swapped out remotely by an ROV. You are literally engineering for 2 straight decades of flawless operation in the dark. Let's check out Section 4, Quality Gates and Testing. Catching million-dollar mistakes.
So how do you actually guarantee that kind of spacecraft-level reliability? Well, you test it relentlessly. Before any piece of equipment even gets close to a drop of seawater, it runs a brutal testing gauntlet. There are 3 chronological quality gates. First up is the FAT, or Factory Acceptance Test. This proves an individual component, like a single valve, works perfectly at the factory. Then we have the EFAT, the Extended FAT. We bolt a few modules together and make sure these subassemblies actually talk to each other before they ever leave the shop. And finally, the big one, the SIT, or System Integration Test.
The SIT is a massive deal. It's a full-scale simulation of the actual installation sequence done entirely on dry land using the exact ROV tooling that'll be used offshore. Skipping or rushing this final phase, that is easily the most common root cause of offshore delays. If you skip it, simple interface mismatches, like a connector being just an inch too wide, go completely undetected. And let me tell you, when you discover that mismatch 5,000 feet underwater, it is a catastrophic problem.
And that leads right into Section 5, Economics of the Deep, the cost of inaccessibility.
Let's tie all this rigorous engineering and testing back to the one thing that drives literally every decision in deep water: the money. If an untested component fails on the seabed, you can't just send a guy in a pickup truck to fix it. A shallow water diving vessel might run you tens of thousands of dollars a day, but a specialized deep water ROV support vessel, that can cost anywhere from $150,000 to $300,000 for a single day. And that is just for the boat. It doesn't even count the millions bleeding out because the well isn't producing.
This is why interface management is basically risk management in disguise. It's like a relay race where you have the fastest runners in the world, but they never practice passing the baton. The handoff is where the whole system falls apart. And what's crazy is that the biggest risks aren't usually the super complex connections. They're the simple interfaces nobody bothered to document because they seemed obvious. Catching a tiny error on paper costs a few hours of engineering time. Catching it on the quay side during an SIT costs days. Finding it in the water, that costs weeks of schedule and tens of millions of dollars.
So you now understand the mechanical body of the hardware, the spacecraft philosophy needed to build it, and those absolutely staggering economic stakes that punish even the smallest mistakes. But getting it installed perfectly, that's really only half the battle. We've built the ultimate subsea system, but it leaves us with huge questions. How do we actually choose the right host facility to receive this fluid? And how do we design bulletproof control systems to manage the whole operation? We'll be unpacking all of that in our next explainer. Thanks so much for joining me, and keep questioning how the world beneath the waves actually works.